Good evening, Doctor Saab. Good evening.
हाँ अरविंद सर गुड इवनिंग एम आई ऑडिबल
Quite audible.
यस यस
Now participants are joining. So we will wait 3-4 minutes. So by 7:05 we will start. Is
ओके
this
सर
okay?
ओके नो प्रॉब्लम
Okay. Thank you.
ओके थैंक यू
Chaturvedi, can we start?
Yes, we can start.
Okay. So, good evening, everyone. At the onset, I would like to welcome today's speaker, Dr. Pradyumna Chaturvedi ji. Dr. Chaturvedi is right now working as an associate professor in the Department of Electrical Engineering at Visvesvaraya National Institute of Technology, Nagpur. Dr. Chaturvedi obtained his Ph.D. in Electrical Engineering from MANIT Bhopal in the year 2010. He is very active in the research field and he published more than 90 papers in various reputed journals and conferences. He also published one book titled Modeling and Control of Power Electronic Converter System for Power Quality Improvements, which is published by Elsevier. Dr. Chaturvedi is also associated with very renowned professional bodies like IEEE USA as a senior member, life member of Indian Society for Technical Education, member of IET UK, and member of International Association of Engineers. Up till he has completed 4 research projects and 3 research projects are still in pipeline, which is sponsored by the DST SERB under CRG. One is related to the Indo-Taiwan Joint Project, another from the Indo-European project. He is also organizing lots of technical activities like various conferences and other student related activity. His research interest includes green energy, electric vehicle, smart solid state transformers, reliability in power electronics, and fault tolerant converters. So with this brief intro, I would like to request Dr. Padun Chaturvedi to start the today's session. Sir.
Okay, thank you, Arvind sir. Am I audible?
Yeah, quite audible, quite audible.
All right, okay. So, thank you so much for introducing me and giving me the chance to share my experiences with the audience, or you can say researchers, which may take the topic of interest uh, for their future research. So, I think, okay, can you see the screen?
High screen mode. Keep in the presentation mode. This is bit.
Yes.
Okay, now it's fine.
Now, okay. All right. Okay.
Yeah, yeah.
Okay. So, all of you, good evening. I think everybody is from India only. So, good evening to everybody. And this is, you can say, the topic. I think this is the fourth day of the FDP.
Yeah, yeah.
Yes, sir. So, the as Urban sir told me that this topic, this FDP is on the power quality uh, mitigation techniques or some issues in the power system. So my area is power electronics. So I tried to cope up with or to match the theme of FDP with my today's presentation. So let us start and hope we will get some new things and all of you will get some new topics, new areas of research. Uh, I think most of you are from some colleges as the faculty member or some are also students. So welcome to this talk or not talk, you can say interaction. So you can ask any questions in between or as Arvind sir will guide us. All right.
At the end of the project, that
All
would be
right.
better because it
Yes,
will
yes.
maintain the flow. That would
All
be
right.
better.
Okay. So I have kept the title of the talk like this power quality mitigation via solid state transformer components for our future smart grid technique. So My presentation will be in three parts basically. So now SST or solid state transformer is not the new concept. Everybody knows about this. So I will just talk about for a few minutes on SST. We will call this as a PET also, power electronic transformer, or sometime we will call this as the smart transformer. If we will apply the IoT applications or smart sensors in the area of this SST. So there is some problem of internet. So just I would like to just turn off my video. Yes, now it is okay, perfect. And second part, I will just discuss about dual active bridge, which is the main component of SST. So as far as we will concern about the power quality mitigation in the power system network. So as the power electronic engineer, multi-level inverters or converters are one of the simple and suitable topology to improve the power quality. This will reduce the harmonic contents. This will also reduce the voltage stress across the device, and so many advantages. And third part of today's interaction or discussion will be on reliability in power electronic converter design, or we can say uh, means if we will talk about different design techniques in power converters, then modern power network will focus on design of power converters by considering the three main factors. Those are: number one, losses or efficiency, obviously. Second part is the power density. So we should be able to develop high power density power electronic converters for our applications, so that we will take a maximum output from less space consumption. And third part is the reliability. This is the biggest challenge also, or biggest you can say most important requirement of modern day power electronic converter based because reliable power supply to be given to the customer or loads may be critical or non-critical loads. So these are the three sub topic of my today's presentation. So first we will just start from our well-known phenomena, that is why we have to go for this SST. What is the need of going for this SST? है ना? So to take this in light mode, then we will just discuss about the traditional transformer. So everybody knows about the traditional power transformer of this shape. It is having very uh, reliable and highly robust structure. It is highly efficient also, and also it is relatively inexpensive. So these are few advantages of traditional transformer, but this will impose so many drawbacks or limitations in power network. Those are, you can say, uh, if now because we are moving towards more and more DC loads. So in our modern and future smart grid network, we are trying to develop more and more DC power sources like photovoltaic and other, and also DC loads, maybe light load, irrigation pumping load, fan load, charger, EV charger. So we can have a different variety of the loads which will require DC power only, DC voltage or DC current. All right, to for their proper operation. All right, and in the present AC distribution network, we are converting this AC into DC using rectifier. That will be pulsating DC, and after that getting the pulsating DC, we have to filter it out. So using we will use the filters which will contain passive elements, inductor, capacitor, and so many things. So this will make system very bulky. So to you can say to mitigate this problem, and to cater the need of the future smart grid, in which we have to integrate a large number of photovoltaic PV array and a large number of EV batteries. So PV and EV, these are the latest trends which we have to integrate into the existing power network. So if we will talk about these future requirements, and also I would like to mention one point here, that in future smart grid network, you have to integrate so many IoT devices, smart sensors, smart communication protocols, smart transmission of the variable or data, है ना, to remote host or remote PC, and observe the variable, remote monitoring, remote control, so virtual control. So all these smart grid features are not possible in traditional transformer based power network. All right, so these are the main weakness of these transformers: no capability of voltage or frequency regulation. So it is also having highly coupled harmonics and other disturbances, and difficult to control the power flow. So these features are not able to be interfaced with traditional transformer without using the power electronic converters. All right. Second drawback is there are no DC ports available in this transformer. So it is not friendly for integration of renewables, EV battery, or any other storage device or medium. And third is the large weight volume. So this will be having very less power density. So these are few features or few limitations or weaknesses in traditional transformers, which is not fit for our future smart grid. So that's why we have to go for some new technology in power network. Before discussing those in more details, now these are some desirable features of transformer in modern power network era. So these are the features which we have to integrate or implement in our design of the converters. So system should be very easy to integrate with different DERs or DES like PV, wind, or any other source. DC port should be available for distributed energy resource interconnection, high or medium frequency isolation. All right, this is also one requirement here. So that the any adverse effect or disturbance at one side should not be transferred to other side, because we have to operate at high frequency, because this will reduce the size of the system. This is to be discussed in details, that uh, inductor and transformer, these are the integral part of any power network. So we cannot avoid or eliminate inductor and transformers from the power network. And we are giving 50 hertz supply to the inductor or transformer. So this will create huge and bulky system. So if we will be able to give a medium or high frequency voltage signal to inductor or transformer, then obviously from the basic design criteria or calculations, we know that the size of the system will be reduced. So in that sense, this sentence is written here: high or medium frequency isolation should be there in future grid. Low weight or volume also required. Other than this, we have to protect the sensitive loads from power system disturbances, from harmonics, sag compensation, outage compensation, low voltage ride through capability. So these are few challenges which we have to take care. And we should be able to protect the power system from low disturbance as well. In terms of this input voltage control through VAR compensation or sinusoidal current from for this distorted or non-linear loads, protection against overload, and fault current limiting and fault isolation. So these are few features which are required in modern power network. but how we can integrate these features in our, you can say, this power network. So this will be very easy, because nowadays you know that most of the attendees are from the power system area, so they know very well that optimization and location finding or placement of some device. So these are few challenging tasks in power system network, and in this we have to use some AI tools or machine learning tools also in that case. So how to implement that thing? So if you are using some digital controllers in our power network, then this will be very easy task to implement such type of, you can say, fault isolation, fault detection, fault compensation, power quality mitigation techniques very easily in the power network, which will be having power electronic converters controlled by some digital controllers like DSP, FPGA, or microcontrollers, or like this. So again, in other words, we can just classify different desirable attributes of modern grid. So high controllability should be there, high efficiency, high power density, and superior reliability. So these are the four major features to be implemented in modern power network. So we will go one by one how we can achieve these four parameters or four features. For example, number one, to achieve the superior reliability, we have to use some. That means, what is the meaning of reliability? As the power electronic engineer, reliability for us, it means if something happens to the switch in the power converter. Ultimately, we have to use some DC-DC converters, some rectifiers, some inverters, all right, in such smart grid. So what happens if one switch fails or two switch fails or multiple switch fails? So we have to develop some type of power electronic converter topologies which will try to mitigate or try to improve the system reliability by giving the full power, full voltage to the load without compromising with the power quality of the system. So in this case, we have to be very careful in detecting the fault, fault detection, and fault clearing. So these are the two main things. So in this case, fast acting fault tolerant topologies for power converters, and it should be also very modular in approach. So this feature we have to develop here. Then how we can achieve the high power density in the converters? So again, as I just told before a few minutes, we have to design for high frequency operation. So inductor and other magnetic components should be operated at high frequency. So this will reduce the size of the converter. And high efficiency, design optimization and loss minimization by using some soft switching control techniques, because everybody knows that losses in the power converter will be due to one fact, that current and voltage will be present during switching of the converter. So switch on and switch off operation will create some power losses. So switching losses will be very large as compared to on state or off state losses. So we have to optimize the design also. And high controllability means we should be able to develop some novel control techniques for some real-time control and monitoring. So all these features are co-related to each other. And these are the very highly recommended practices in modern power network. So to take care of these features, now this SST concept is developed. It is not the new concept. It was well known before, around during 1970s, 80s around. But there were some problems in developing high frequency converters or there were no switching device available which can tolerate very high frequency in kilohertz or 100 kilohertz or like this. So these were not popular, but due to because we have to switch the switching device like MOSFET, IGBT at high frequency like 100 kilohertz or sometime 1 megahertz also. This was not possible. But nowadays we are having wide bandgap devices like silicon carbide and gallium nitride devices. Now GaN FET is also there, GaN FET. So we are able to switch at 1 megahertz switching frequency also with some medium voltage or medium power level also. It is not used in practical case, but it is in research case, research means area only. But some 20, 30, 40 kilohertz switching converters are already available in some industries. So due to the development of these switching devices with low on state resistance and very low turn on and turn off time, because if switch will take more turn on time and turn off time, then the overall average switching loss will be increased. So these wide bandgap devices are giving very low on and off time delay. So the switching loss will be reduced. So to take care of these things, these are the stages of SST developed already. So in 1970s, this was the case. Here we are having high frequency isolation here, AC to AC single stage, but they used only SCR in that case or GTU. Then in second case, we are having one DC link voltage here, and in third topology, we are having one DC link stage here. So isolation at high frequency is at front end, and here this is at back end or load end. And this is the most commonly used topology, AC to DC, using one rectifier here and filter, then DC to DC with high frequency isolation here, and again inverter DC to AC. So this is the most widely used topology. So DC to AC, so this will contain one inverter here at front end, and again one converter at back end. So this will be having AC DC, DC DC, and DC AC system. So this three stage SST is most commonly used, because you can see from this figure D that you will be having two DC buses here, one at one level of the voltage and second at second level of the voltage. So nowadays you cannot predict the EV charging, how many batteries are to be integrated in next 1 hour, 2 hour, or 3 hour, 4 hour. So load prediction you cannot say. So what we can do in such type of system, we can reconfigure this system. So depending upon the voltage requirement, you can integrate DC source or DC load at this DC bus or this DC bus. So all things will be only in the control side. So these are a few advantages of SST over traditional transformer: high power density, instantaneous voltage regulation, power factor correction, outage compensation for isolation, DC ports available, power quality monitoring and control, because we have to because we are able to monitor and control the variables through our digital controllers. Availability of DC links, this will facilitate the RES integration and easy interface with all communication and smart grid network. And most important is this much: bidirectional active and reactive power flow control. All right. So because in this type of system, our converters are of such topology that they are able to flow the power in both directions. So all are bidirectional power. So this is very easy to control the power flow between source to different loads and storage medium in between. These are few very now you can see this list. There is no feature or there is no main requirement of modern smart grid. है ना? So all features are incorporated in this SST. All right, these are few only, but we can add more also, like protection. है ना? It is very important issue in power converter based systems. So like this also, you can develop MBDC, HVDC grid also, and connection to the medium voltage like this. All right. So this SST is not suitable for any application. All right, because this will be having a 2 or 3 stage converters. So we cannot use this anywhere without thinking anything. But the applications which will require very high power density with good efficiency and reliability, there we have to use this. And also which will require DC ports to integrate different DC source and DC loads, and also storage also, like military applications, remote applications where grid is not available. So defense applications, military applications, space applications, है ना? Or ship applications, navy applications. So these are few area where this is very important to discuss. All right. Now we will come to our main topic now. So after having this brief introduction about SST, now these are the control objectives which we have to focus from the power quality point of view in power electronic converters, because all these converters are non-linear loads or non-linear components. All right. So control is a little bit complex in this case. So front-end converter, isolation, and inverting or back-end or load end. So primary objective of this front-end stage is to control the medium voltage DC bus or this bus during load variations and three-phase MVAC currents. So any disturbance at load side will come to this DC bus, and source side disturbance will come through this AC bus. So this rectifier or this stage will control or regulate this DC bus voltage, and this will also improve the supply current power quality in terms of harmonics and power factor, and other parameters will be improved from these three parameters: DC bus regulation, its ripples, supply current harmonics, and supply current power factor. Now this stage, this is having the primary objective to control the LVDC side bus regulation, and this will decouple input to output stage. All right, so this is having these two main primary objectives, so that any fault or any disturbance at one side will not propagate to other side. And this load and converter stage will be having this primary objective of controlling the voltage and frequency in LVAC grid. So this will take DC input, and this will synchronize this supply with the main AC grid at low voltage level. So these are few primary objectives, and secondary objectives are, we can say, so these primary objectives will control these objectives: active and reactive power flow control, and unity power factor regulation, and balanced sinusoidal currents. And this stage will be able to control the power flow in both directions. We will see how this will be achieved here. So in both directions, just by controlling a single phase shift angle, we will be able to control the power flow with good power quality as well. That topology we will see. And the integration of the DC microgrid with EV charging. And this load and converter stage will regulate the power quality, and also this will reverse the power flow control as well. So these are the few control objectives which any researcher also can take these as the main research objectives also. So these are the application areas already discussed: the fast charging stations, onboard ship, solar park, wind farms, electric traction drives also in aerospace. So this SST is applicable to now in every application which will require high power density, high efficiency, and high reliability. All right. So this part I will just yes. So this diagram will just to show the idea about how to use this concept. This is the main grid rectifier. Then this is the DC-DC stage here, like this here. As we have seen in this diagram, this is stage, second stage, and this will generate some voltage 400 volt, or you can say sometime if we will be able to use high gain DC to DC converter, then this may be 650 volt, 800 volt, or higher than that also if required. And then we can give this to different DC converter here, and this can be given to the EV battery, and again we can store this as the backup here also, and PV also can be connected here. So this is not having any inverter stage at the back end, so we can stop only at this DC level only. So this is also one type of fast charging station using this SST concept, and if required then we can integrate this output to the main grid as well if required. So vehicle to grid or grid to vehicle, those applications we can very easily implement. All right. So now just we will just have a look on yes, yes. Just a minute. Please give me 1 second. All right. Okay. So I will not focus on the traditional dual active bridge because everybody knows about that thing. So I will focus on main good power quality dual active bridge only. So here now we can see here this SST. This is the uh, structure of the SST. So this will contain one rectifier, one inverter. So this will be generate high frequency AC signal here to the primary side of the HFT, and secondary will be also at 100 kilohertz or more than that, and rectify this we will get DC then AC. So this SST concept has, you can say, has emerged as the 10 most emerging technology by MIT USA in 2010, and in 2008 this Freedom Center from NCSU USA and Cal University Germany and KTH Zurich. So these are the laboratories where, and also Virginia Tech USA. So these are few laboratories which started working since last around 15 years in this. But recently, in the last 5 to 6 years, this uh, technology has taken interest among the researchers in our area, that is power electronic converters design. So this part means this work has been done by my student Deepesh. So he has done as the job as the GRF, and he has also submitted the PhD thesis just before 2 months only. So this topology we have taken and published in 3 IEEE transactions already. So this is the topology which I would like to just mention here. Here AC you can take here, then you can use one uncontrolled DC here. In this topology, just we have taken for simplicity only uncontrolled DC to make the DC link only. Then we will use this buck boost converter here, and before giving to the transformer, now this is, you can say, four MOSFET lag. So three level type of lag we are having here with separate DC link capacitor here, and this half bridge will be given to this HFT here. This is to second HFT, and secondary will be isolated here. So we will be having separate DC link voltage here. So this we can regulate to 800 volt, 400 volt or 100 volt also as per the requirement here. And if required, then we can connect these two ports together in series or parallel to make current or voltage increased. So this is the bidirectional buck boost type of topology of SST. So here what we can suggest, what we can do here, in this case the design of inductor, design of this transformer, and design of this leakage inductor here LS and this CS. So these are the prime important parameters in this bidirectional three level buck boost converter. So this is the new topology. So here what we can do, this will be having some inherent soft switching performance. All right, but we know, as we know that these passive elements L and C will be having some resonance phenomena at some particular frequency. So that means they will be only resonating at one frequency. All right. So to take care of this thing, the biggest challenging task in such type of system, which will be incorporating power electronic converter switches, passive elements, inductance, capacitance, some resistance. In such type of circuits or components, we have to take care few issues, because we have to talk about only three parameters. Before developing this type of topology, we should be able to implement a converter with high power density, high efficiency, and high reliability. These are the three main parameters without compromising the power quality of the power network. All right. So this will be giving you can say three level type of waveform. So the harmonics at the transformer side will be reduced in this case, and also the ripples at DC link will be also reduced. All right. So study will be given after this on various aspects of this. So by this mode, so just we can just divide the different mode of operations of this converter, and by having the different mode of operations of this converter, now what we have to do, we can divide this in different modes, mode number 1, 2, and 3 and 4, like this, and we can write down the KVL in each mode here, and the primary performance parameter is that this is the ripple current here in inductor. So ripple current in inductor is the crucial parameter which we have to control. So in different modes, we have to formulate the ripple currents in the topology. I am giving only for this topology. We can also show the same thing for other topologies, two level topology or other topology as well. So these ripple currents will depend upon bus voltage, input DC link voltage, duty cycle, inductance, and switching frequency of the converter. So now we can see. So each of these will be changing as per the mode of operations. Maybe from power flow from source to load or load to source. Now what we can do here? So here we can do one thing. Suppose, for example, we are trying to develop this type of converter here. This will be having good power quality as well because of the 5 level topology here, not 5 level, 3 level. So in this case, again, I will repeat, we have to take care a few parameters or a few performance indexes in power electronic converters design. Those are efficiency, power density, reliability, but not compromising with some other parameters like voltage gain with change in the duty cycle. So what we can do, we should be able to achieve those parameters without compromising or without any limit on the voltage gain range. So if you will change the duty cycle from 0 to this 1, then we can plot this gain of the converter with D variation. So we can see that for different RL upon R, RL is the load resistance and R is the, you can say, leakage inductance. So by having this ratio here, RL upon R, now we can have this 0.01, 0.04, now 0.2, like this. So, and this is for 0. So if we will make RL upon R equal to 0, this ratio will be 0. Then this will go up to infinite gain. So in some practical cases, for 0.01, 0.016, 0.02, or 0.04, or 0.01. So if we will try to do like this, so then we can say that the gain achievable will be increased for reducing this gain, this thing. All right. So that means for increasing of this thing. So that means maximum gain will be achieved at this point, for example, 0.01 at this D, and for D will be increased so that you will be able to achieve more gain here. All right, achieve more gain here. So in other words, we can see that D is increased and gain will be also increased in this case. So this will depend upon the ratio of resistance of inductance to the load. So these are again some different mode of operations here. So now, yes. So in this case, what we can do, we can just try to develop some soft switched LLC based dual active bridge converter here. So this is nothing but the 3-level type of lag here to improve the power quality of the harmonic contents in the AC network. So these are the few design considerations we can take care. Leakage inductance, and second is the parasitic components of HFT. So we should be able to incorporate or compensate for any parasitic component present in transformer, inductor, or also in the switch. So all the parasitic elements should be compensated in the design of the converter. So design of the resonant tank circuit elements like this LLC. So this will intervene HFT parasitic components and influence of tank circuit configuration parameters, resonant capacitor rating, soft switching operating range, and selection and design of HFT, and most important, selection of the switches. So each of these design steps are important. Nothing, no parameter we can ignore, nothing. Each of this we have to take care in the design side. So now this is the graph we can take. This will show the output power with voltage ratio. So this will give the idea about the different value of inductance in the transformer. So this graph will show that primary side hard switched and secondary side hard switched, and here Both bridges are soft switching. So we can say at voltage ratio 1 is to 1, voltage gain is 1 is to 1 in this transformer. Here, if this is 1 is to 1 transformer, then we will be having both side switches will be soft switching. Soft switching means either current or voltage will be zero or will be made zero forcibly, so that V into I or power will be zero at switching. So turn on and turn off switching losses will be zero. So it is called soft switching here. So and if we will just to change this voltage conversion ratio, suppose 1 is to 2 or 1 is to 1.5 or anything other than 1 is to 1, then either secondary or primary side switches will be switched under hard switching mode. So switching loss will be increased. So what we can do here, we should be able to design our inductance and capacitance and transformer design to be taken care. So this part, this passive component part is the crucial stage of the design. So this we have to take care. So that we have to take care so that the range of the voltage conversion or soft switching should be large. है ना? So output power. So you can see here, if output power is less than 0.5, all right. So if you will go here beyond this, है ना? Go beyond this with this voltage conversion ratio 0.7, go beyond this power level. So you will get soft switching in secondary side, but you may get you may get hard switching at primary side if you will achieve this gain here. So we have to make some trade-off between voltage conversion ratio, step up or step down, and output power requirement with the system efficiency. So all this is to be designed by taking care of these parameters or these few issues. So we can say that higher leakage inductance will offer wide soft switching range for low power level. So we can change the leakage inductance of the transformer design. All right. So that this will give the changing voltage conversion ratio as well. Increase the RMS current in the primary and secondary winding of HFT. A small leakage inductance can offer maximum power at a small phase shift. So it is again one issue which we can optimize. To have better control over the power transferred, large inductor is required at high value of phase shift. Now phase shift is nothing but you can see here. This is one primary side of the transformer, one H bridge here, second H bridge here at secondary side. To make the power flow between this side to this side, there is a basic concept that there should be some phase shift angle difference between primary voltage and secondary voltage, है ना? So Vs and Vr, sending and receiving end voltage. If these two voltage will be in phase, then power cannot flow. So to make the power to flow from left to right or right to left, we should provide some phase shift angle between these two voltages. And this phase shift will be created or implemented by giving the control pulse to S1, S2 and S1 dash, S2 dash. So S1 and S1 dash will be having some phase shift angle. So this is the meaning of this phase shift. And soft switching range is also maximized when voltage ratio will be unity. So this is again visible from this. So now how we can optimize this LLC tank, because this is the most important part which will take care of the power quality of the SST component. So here we can see one thing in the design side, we can have this thing leakage inductance HFT. So this is giving you the traditional dual active bridge converter equivalent circuit to achieve ZVS 1:1 ratio. Then this is the optimal LLC based resonant tank circuit. All right, in this case. So here we can just optimize this L and C value here. And this is the modified dual active bridge converter, which will employ the optimized LLC based converter. So the number of turns in the HFT, this will offer the parasitic inductance and capacitance across both the windings. So what we can do, if this HFT will be having parasitic inductance or capacitance, that can be compensated by equivalent inductor or capacitor in series or parallel here. So that parasitic effect will be compensated through these type of additional value of capacitance or inductance here. So it is the simplest way of compensating for that thing. So how to design the LCC resonant tank circuit uh, for that parasitic effect element of mitigation? So this is the simplest, you can say simple mathematics we can have. No need to discuss actually. So based upon this simple mathematics, uh, resistance, Q factor, frequency, and resonance frequency, all we can calculate for any converter, and also AC resistance also we can find out. So this is the you can say concept or formula given for this gain M with normalized switching frequency. So this graph will give the idea about resonance in our LLC based converter, because now system is becoming more complex now, because in this SST based system now we are trying to optimize some parameters: efficiency, power density, reliability, now voltage conversion gain, है ना, कितना कर सकते हैं स्टेप डाउन एंड और स्टेप अप कर सकते हैं, how much voltage conversion ratio we can achieve, and then gain also that is equal to gain. And now next uh, next variable is coming now in the picture, switching frequency. So we have to optimize gain and frequency of switching both. So we can see at one frequency gain will be maximum. If you will try to increase or decrease the switching frequency, then you will not achieve maximum gain. All right, and also Q is fixed, है ना, and also this K term. So this K term will be also different, है ना. So K is the constant 8 upon pi square in this topology, and here it is 2 upon pi square here. So this K for different K, Q is constant, and for K constant, different Q. So for under different conditions, we can plot this thing. So what we can conclude from this figure, that is, you can achieve gain maximum only at one particular frequency for any Q or any K constant. So as this is similar to that MPPT or RLC series resonance. So here the bandwidth will be somewhat narrow in this red, all right, and this bandwidth will be large for this blue, or k equal to 4 or 3 also. So the bandwidth means the soft switching range of the converter will be controlled by the switching frequency, or in other words this K or Fn, or in other words this will be governed by duty cycle, frequency, L, C, and other passive elements. And overall This will be governed by the parasitic elements of the converter, switches, and all passive elements like inductor or transformer. So this is the most important part we have to take care. Now next is this. Now we will see the significant effect of rectifier configuration on the converter gain. So which type of rectifier we are using here? So that full bridge or half bridge? Full bridge or half bridge? So this will give the just basic comparison only for full bridge and for half bridge. So we can see here, we can see here that gain will be this much G max for half bridge, and for full bridge this is obviously you can say near about double to this half bridge. It is obvious. So this frequency of operation will be changed from this side to this side. है ना? So what we can say here, we can do one thing. If we will implement this full bridge here, if fault occurs in one switch, then this will be converted into half bridge. All right. So we will add these additional capacitor here at the output side. So we can reconfigure this converter which can operate at edge full bridge or half bridge. So changeover from full bridge to half bridge will take place. So this will be implemented through only digital controllers. So we have to make some flow chart, we have to decide some logic, and we have to make some algorithm for that, under what conditions, under what requirements of the gain or frequency. We have to operate this as full bridge or half bridge, है ना? Or under faulty condition in any one switch out of these four switches, this parameter is need to be optimized out of these. So all this will require not very detailed but simple basic calculations or basic idea. All right. So now this is the designed inductor and transformers in the laboratory. So it is only inductor here. So this is the input inductor in that converter with value 2 millihenry, and RL will be 340 milliohms. This is, you can say, 51 microhenry, and RL is 150 milliohms in LLC converter. This is the HFT with turn ratio 1:1, and this is the pair of series resonant inductor and HFT here. So these are the inductors and transformers used in this topology, and these inductor and HFT were made by using sandust core and some bridge wires, and bound by student in the laboratory. Deepesh has done this thing in the laboratory, and this was working fine. So this is the developed prototype already. He has developed this thing and got some good publications also, and submitted the thesis as well. So all right, so just a minute. So 4 kilowatt converter is developed in the laboratory using these parameters. 104 kilohertz is the switching frequency, and 2 kilowatt as one port. Total 2 ports will be of 4 kilowatt of 400 volt each with 5 ampere rating like this. And he got some good result also in the laboratory, like this phase shift angle variations. I would like to show again. Yes, here you can see here we implemented one adaptive control algorithm in the laboratory in the DSP 28379D. This is the phase shift angle actually, है ना? So you can see these two waveforms, blue and this one, है ना? So these are the two waveforms with some phase shift angle. It is equal to 48 here. All right, it is 48 degree here. and after changing of at this transient instant, load will be suppose reduced here, है ना? So at this moment load reduced. So how this will be taken, this adaptively, load reduced. So this current, load current is reduced now, and to take care of this load reduction, the phase shift angle is changed to 22 degree automatically, adaptively. All right, you can see the change in the phase shift angle here, and again load again increased here, still reduced. So after this thing, and after some time, for example, we can change the load as well, or also we can have the power flow reverse also in that case. So this will show you the waveform which will give you the power flow reversed. All right. So at any instant we can change. So the phase shift angle will be changing from 0 to 90 or 90 to 180 degree. So if phase shift angle will be more than 90 degree, then the power flow will be reversed in that case. So for this, this dual degree control scheme will be was implemented in the laboratory. So no need to discuss further on this technique. Yes. So second part, just I would like to just talk about this reliability part. So if any doubt or questions, we can discuss now based upon this discussion. Otherwise, I will just start the second part of the lecture. So we can take a break of 2 minutes. In between, you can ask the questions also. If allowed.
Yeah. Anyone? Is there any query or question on the first part? You can ask.
Acha, Arvind sir, these are participants are from which background basically?
Electrical मतलब electronics, power system, both areas.
Okay, okay. So this is the difficult time actually, है ना? In the evening, dinner time is also there.
No. Here the dinner
Yes, yes.
time is late.
Mm-hmm.
Anyone is having any question? I think there is no
Okay,
query. So
no
if you
problem.
want, you
So
can start.
yes, yes. So we can just go ahead. All right. So just a bit. I will take a 30-second break. Okay. All right. So I hope this is not very heavy. That part was not very heavy. I hope, because I have not added highly mathematical derivations in the presentation. So just I had only tried to just give one topology of a multi-level dual active bridge for power converter for our future smart gate, that is called SST. So now this part I will cover on reliability part. So reliability can be improved in two terms. Now, number one point, if we will be able to develop some new topologies of power converters that will be having some optional or redundant switching states or devices in the converters system. And second, in the existing system of power converter, if we will be able to implement some modified control technique, है ना? So that under faulty condition, the faulty switch will not receive any control pulse, and some alternate or spare power device, healthy device will take the power pulse, and that will compensate or that will give the power to the load. So these are the two ways. So this is the modern grid. In this modern grid, you can say, yes, in this modern grid, uh, we are having AC grid, then one MBAC bus, then one rectifier, then second one DC bus here, one dual active bridge, having DC to AC, then HFT, then AC to DC. So again now DC bus, second DC bus, and again inverter, and give this AC to second grid. है ना? So this is the power network which will be used for integration of two grids at different voltage levels. This may be one application of this SST. This part is called SST here. So we can integrate wind energy through some converters, solar energy through some converters, battery, ultra capacitors through some converters to the common DC bus. And second DC bus can be given to EV charging stations, traction loads, or some domestic loads, and so on. It is just one conceptual diagram only. We can just you can say relocate the source and loads, है ना? As per the need of the source and load and grid as well. So this is the complete self-sustained microgrid, or you can say smart grid, है ना? So because we are having so many converters to control these power flow, so it is very easy task to integrate smart devices, IoT devices for remote monitoring and remote controlling, virtual controlling of every variable, current, voltage, power factor, losses, efficiency, है ना, voltage conversion ratio, everything can be controlled via remote control, virtual control through this. So in this case, now in this part, just I would like to highlight uh, different fault tolerant multi-level inverters. So this is the main content I would like to introduce to improve the system power quality and reliability together. So these are the challenges involved in SST implementation. Issues with SST topologies, voltage balancing issue, because in SST we have to use some capacitors. In multi-level inverter topologies, we have to use so many capacitors. So problem is there to balance the voltage across each capacitor, power balance, protection, and reliability. These are few issues which we have to focus. So I will not cover traditional multi-level inverter topology because everybody is now familiar with all MLI topologies like neutral point clamped or diode clamped converters, flying capacitor converters, H-bridge converters, and MMC. So these are having some type of multi-level structure, है ना? So I will not cover those things in details, but in this next part of the talk, I would like to introduce some type of topologies having fault tolerant feature. So for example, this is one H bridge here, है ना? So this is the five level topology. S1, S2, S3, S4, these are forming one simple H bridge. It is the simplest topology. And this S5 is the bidirectional switch, having one control switch and four diodes. So if we will connect this to this load or this lag, then this is forming a five level converter, having output voltage plus 2V, V0, minus V and minus 2V. So this is giving you the five level output. Label means this is, we can see here. Label means this load will be having 0 level, V level, and 2V, and negative, minus V, and minus 2v. So in one cycle this will be having plus 2v plus v 0 minus v minus 2v. So 1 2 3 4 5 levels. In one cycle this will be having 5 level of the voltage. So single phase 5 level converter, T type topology. So in industries what they are doing basically, if fault occurs, so to improve the system reliability they are using one spare similar H bridge, है ना? So they are using some spare stack of H bridge. So this is very costly. So we have to you can say put a double cost. We have to spend double cost to improve the reliability of the system. So but here we can see this is the starting topology only. So Sai Krishna, one of my student, he started working on this. So I told him to do this thing, and slowly we will do some mathematics in this converter. So within next 40 minutes, we will try to just see different topologies of this, and improved topology. So here we can see one thing, this is the relay here, and one relay we can use here. So these are the complementary relays here. So this will give the switching states here. So R1 will be on or off depending upon the labels, missing labels here. So S1 to S5 out of these things. So these are the switching states of a proposed FTMLI1. So this is one topology FTMLI. So if this will be opened, then this is out of focus, out of the picture. It is opened. So then this system will be out of the, you can say, out of this circuit here. So any one level can be shifted from 5 level to 3 level here. Now here what we can do here, in this case, switching states of proposed FTMLI1 at different fault conditions. Faulty switch may be 1, 2, 3, 4, 5. So now we will just try to explain if fault occurs in switch number 1, 2, 3, 4 or 5, then what will happen? So state numbers are there. If fault occurs in switch number 1, then plus 2b label is missing, not available. Then plus b is this 3, then 0, 5, 8. So output levels are 3. So 3, 5, 8. That means 3, 5 and 8. So these are the states used to give the output level 3. So this S1 is faulty. So what will happen? तो क्या करना पड़ेगा हमको? So 3 means this R1 is closed. 5 means R1 closed. 8 means R1 closed. So if fault occurs in S1, then we have to close this R1. So current will not go through this. It is faulty. So this part will take care of this thing. So this load will take this part, right? R1 closed, so R1 dash opened. These are complementary. So we will get plus V or minus V or 0. So like 3 means V, 5 means 0, 8 means minus V. So this will get 3 levels in the output voltage, not 5 level. But and half voltage will be achieved. So in the same way, in the same manner, if fault occurs at switch number 2, then again this level is missing. So 2, 4, 9 states 2, 4 and 9. So these states will give you the 3 level. So this is the simplest topology, but in this case we are losing the level. So as we know that if we will try to increase the number of levels, 2 level, 3 level, 5 level, 9 level, then the rate of change of voltage in one level change will be reduced. So we can use less rating device, THD will be also reduced. We can get more power, all right, and more voltage can be developed by using less rated device. So these advantages will be not available in this topology here. So in every case, we are getting only 3 levels here, है ना? And voltage amplitude is only half. All right. Only in this condition, you can see in S5, if S5 is faulty, है ना? Then only we will get plus 2V or minus 2V or 0, 3 level, but voltage will be full voltage, है ना? If this S5 is faulty, then we will get full voltage plus 2V across the load, but 3 level. All right. So this is the drawback of this topology. So what industry is suggesting, they are using this tape changing transformer at output end of the converter. So what they are doing, if 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 for example fault occurs in S1, S2, S3 or S4, in that case this load will get only half power, either VS2 or VS1. If S1 or S2 faulty, then we will get VS2 in the load side. If S3 and S4 are faulty, then we will get VS1 at the load side, means half of the voltage of the supply voltage. So this is the drawback, है ना? So what we can do, we can develop one simple circuit to improve the system power quality and reliability. That is, under faulty condition of S1, S2, S3 or S4, if we will be able to boost the voltage before load, then this will give one control degree of freedom, है ना? One additional control degree of freedom, है ना? So this tape changing transformer will do that thing. So under normal operation, this will this R4 is closed, for example, है ना? If some fault occurs in S1, S2, then voltage will be reduced half. So then we can turn on this R2, है ना? So more voltage can be given to the load here, है ना? So just by tape change, offline or online tape changing transformer, we can use this thing, but it is not practically feasible or efficient way of doing this stepping up or boosting the voltage. So what we can do, so this graph will give that idea, voltage and faulty condition. So under faulty condition in switch S1, है ना? S1 is faulty, then by using the tape changing transformer concept, boost this. See, this is the 5 level voltage. This is the 5 level voltage. This level 2, half, 0, minus V and minus 2V. So 5 levels are there, and fault occurs in S1. So this will be delivering full voltage, peak voltage will be constant, but 1 level, 0 level and negative level. So 3 level only, 1 level, 2 level, 3 level. Here 5 levels. So levels are reducing. So Ph.D or harmonics or power quality is poor in this case, but still we are getting full power, no problem. So load will receive full power, but with some reduced power quality. So we have to compromise with the power quality here. It is the main drawback of this topology, है ना? Like this, if S5 is there, then again the same case will be there, है ना? So now this is the second topology. So we are trying to improve the system power quality and reliability together, because in the power quality converter design, we have to focus on system reliability and power quality at the same time. We cannot compromise with any one performance parameter. So this may be one second topology here. So you can see these are the two switches having the capability of power flow in both directions, two capacitors, one source. All right, load is connected here. So in this case, we will achieve different amplitude of the voltage. This Vs by 2, 0 and minus Vs by 2 or minus Vs. Again 5 level. So this is again single phase 5 level topology here. Now, what will happen if fault occurs in any one switch? So this study reveals this thing. So this work has been done by Sai Krishna, and he also got 4 FCI papers, including in transaction and IIT and some other good reputed journals. So if fault occurs in switch number 1 or 2, 3 or 4, 5 or 6, then what will happen? So here we can see these voltage levels will be achieved by these switching states 2 or 3, 4, 5 or 6, 7 or 8 or 9. Those states are from here 1 to 9. है ना? So just given these different you can say redundant switching states to achieve the same voltage level here. 0.5 Vs, 0.5 Vs can be achieved by these two alternate or redundant switching states. Zero level can be achieved by these three state combinations. So by taking care of these things, we can obtain different voltage levels here. So you can see if no fault, then we will achieve 5 level. If fault in 1 or 2, then 3 level. S3, S4, 3 level. 5, 6, 5 level. So we can see that if fault occurs in 5 or 6, then we will get full 5 level output voltage. Otherwise, if fault occurs in 1, 2, 3 or 4, then we will achieve 3 levels. So sometime we will get 3 levels, sometime we will get 5 levels. है ना? So in this case, sometimes C1 will be giving the power, sometimes C2 will be giving the power. So the main problem is that again third challenging task, that is how to make C1 and C2 perfectly balanced. So in the control technique, we can apply that concept also. So uh, there are 2, 3, 4, 5 or so many parameters to be optimized, like power density, efficiency, reliability, voltage balancing technique, है ना, like this, or power quality as well. So how to make some trade-off between these three? So this is again now second next issue, voltage balancing of capacitors. So how to make this? So just sense the voltage VC1, VC2, and just try to just compare these and VC1, VC2, and this SF, that factor. Then if fault occurs, then if fault is in switch 5, yes, then generate the pulses using levels number 1 to 589 as per table 1. This is the table 1. Hmm? All right. So we can just make some lookup table type of system in the controller, and we can recall that as per this control logic here. So based upon this control logic, we can generate different type of switching states, or we can say we can recall different switching states from this table. So this is the important table which we can store in our controller. So after having these different switching combinations or redundant, yes, anybody want to ask something, or it is by mistake?
Sir, it is by mistake only.
All right, okay. Okay, I am expecting some questions if you are getting something from the lecture. All right, okay. Otherwise, I assume that it is means a very typical or complex lecture. Okay, we will try to discuss something. Okay, so what we can do for this circuit, we will have to pre-store this lookup table in the controller memory, and we will recall that as per this logic or this flow chart under different conditions, and then this PWM pulses will be changing continuously as per the switching table number 1, based upon different conditions. So this will give the perfectly balanced system. So then after having this discussion, then we can have IGBT loss calculations, then switching losses, switch on loss, switch off loss, and then we can find out switching energy also, है ना, in the switch. Then in the diode also we can do the same thing, diode on time off time losses. Then we can find out total power losses and then efficiency as well, है ना. So this is the diagram which will just give the idea about how to generate the control logic in this source voltage, two capacitors, this topology, simple topology. I am not focusing on some difficult topology, simple topology, 5 level, fault tolerant MRI topology, which will give the good power quality and good reliability in the power network. Single phase only, low power level and load here. So read the output voltage and current here, and these are given to this control mode selection unit here. So VO and IO will be given here, and based upon this control logic, this flow chart, this will generate this SF056 or SF1 and or 2 or 3 and or 4. So these are the switching states stored already here. So see, we have to pre-store 3 level and 5 level control logic in the controller, maybe FPG or DSP or microcontroller. So these are the pre-stored waveforms. 2 reference carrier waves, 1 sine wave, 5 triangular carrier wave at high frequency, and 1 reference wave here generate the pulses here and here. So these are the pre-stored type of thing, है ना. But main thing is this much, control mode selection unit. So based upon inputs given from this table, an input given by sensing the faulty switch in the converter, and depending upon VC1 VC2 value and faulty switches and balancing algorithm, now this will try to generate this thing. So this switch, so switching will be among 5 level or 3 level control logic. So this converter will be operated in 3 level or 5 level mode depending upon the faulty switch. So this is the main thing here. So this changeover will take over automatically, है ना, 3 level to 5 level. So after having this logic, sometime now see under faulty switch conditions of one switch combination, it is 5 level now. Again you can see here 1 level, 2 level, 3 level, 4, 5 level. Then if fault occurs in S1 or S2, then what will happen? This will go into 3 level case, है ना, but 3 level with full voltage amplitude. So fundamental voltage will be same. So we will get full power at the load side, full power. All right, but at the cost of less, or you can say, but at the cost of increased power harmonics or THD. है ना? So power quality is reduced, but you are getting reliable or continuous power supply here. All right. In the same way, and for this S3 case, faulty case, again 5 level to 3 level, THD increased, power quality poor. But we are getting full power. So reliability, but with poor power quality. Again here again poor power quality, but with good reliability. And in some cases of faulty switches, we are getting same 5 level with full power. So good power quality and good reliability. So we can conclude that in these topologies, In these topologies, you can say we can compare those depending upon number of IGBTs, number of bidirectional switches, diodes, capacitors, DC sources, and reliability during open circuit fault in any switch. So depending upon these tentative or considered parameters, we can compare so many topologies. है ना? So this topology is but compared with so many recently available topologies. So we can have this 4 IGBTs, 2 switches with bidirectional switches parameters, no diodes, 2 capacitors, 1 DC source with a good reliability in any switch faulty case. So this topology is considered as very good topology, and Sai Krishna has done a good work in deriving the mathematics and everything here. And switching loss is also 2.17 comparable switching losses. Conduction losses also comparable, higher than this at 5 level, like this and this much. And efficiency also you can say comparable, not very bad. And THD also you can say in 5 level 20 around, and 5 level and 3 level means 45 around. All right. So but reliability will be improved with this poor power quality. So we have to make some trade-off between reliability and let's say power quality as well. See, I'm just focusing on these different topologies because in a modern power network, we should focus on power quality, power density, efficiency, all these together. We cannot compromise with any one factor. So, like a power system engineer can work on voltage sag compensation, soil compensation, active filters, STATCOM, DSTATCOM, DVR, UPQC, and so many things. So, ultimately, you have to use power converter there. Maybe in active filters, shunt, series, hybrid, UPQC, or any other power quality compensation technique. Ultimately, you have to use some power converter or inverters, and those are the inverters which will contain some capacitors, some inductor in the circuit, and based upon the compensating current or reactive power requirement at PCC or point of common coupling, you have to inject some appropriate amount of reactive power at that PCC through the power converter. So these are some topologies which will give you the improved power quality voltage with good reliability. है ना? So these are very useful topologies for PV applications or EV applications used in rural areas, remotely located areas where there is no grid available. So this is the third topology. Sai Krishna has done a good work, very good work. So he keep on thinking on some new topologies and discussing with me so many times like this. So he was not satisfied with two topologies, so again he developed third topology. All are published already in some good journals. So third topology now. So maybe it is having more number of switches, but still this will give you good power quality as well. So again, these are the three legs of the single phase legs, two switches, 8 and 9 with bidirectional features. Now in this case, now we can see this. Total number of labels are 5, but the main thing is that each label we can achieve by more uh, redundant switching states. है ना? Like plus 2V can be achieved by these 3, V by these 4, 0 by these like this. है ना? Minus V and minus 2V. So now we will come to this one by one. So what will happen if a fault occurs in switch number 0? No fault. 0 means no fault in any switch. Healthy condition. Switch number 1 is faulty, 9 is faulty. So what will happen if fault occurs in switch number 1, 2, 3, 4, 5, 6, 7, 8, 9? So we can see here output voltage available here. So in all the cases, we are getting 5 labels except this one, switch number 5. 5 means 5 kahan gaya? Ye. This is the 5 number. So if fault occurs here, then only we will get 3 labels, because this will not be able to, you can say, connect this to here or to the load, through this load, to load. So in this case, we will get only 3 labels. Otherwise, we will get 5 labels under any single switch fault. Single switch fault. है ना? So just now I will just go quickly. Now this is the testing of the circuit under two switch faulty case. In the topology second, we have not considered two switch fault, single switch fault only. But here we are considering two switch fault case also. So what happens if fault occurs in switch number 1, 2, 1, 3, 1, 5, or 1, 7, 1, 9, or 2, 4, 2, 5, 2, 7, like this, or 3, 4, 3, 5. So for some combinations of faulty switches, we have tested this circuit. So under again two switch faulty cases, now we are having almost in all conditions 5 label except this third, 7 and 11 serial number, है ना? So 1 5, 2 5 or 3 5. See, fault occurs in 1 5, 2 5, 3 5. 5 is common. So that means if fault occurs in switch number 5, then only we will get 3 label, otherwise we will get 5 label output voltage with good power quality. Yeah. So this is the condition. All right. So these are again next switching combinations of different two switch fault conditions. So for around 26 combinations, Sai Krishna has tested this circuit and it is working fine. So these are the parameters for the result simulations. So again, under some faulty conditions, we are getting 5 level, good power quality, good reliability. In some cases, good reliability, but with some poor power quality. So these are the same things. So he developed 3 more topology, but I am not showing here. All right. So these are the topologies used to be applied in so many applications like PV, EV, vehicle to grid, grid to vehicle, or so many applications. And this is the last part. Just briefly, I will just introduce you how to analyze the reliability of the power converters under different faulty conditions. Yeah. So to discuss this, this is the Markov chain model or Markov chain theory, and to develop this theory, we used that military handbook of reliability. All right, in that we have to define some reliability factors. So for example, this is the normal operation here. We can just have this on a normal operation. Then this is the, you can say, burn switch fault or some faulty case, and this is the complete failure here, failed. So normal, faulty, and this is the complete failure. So using this Markov chain model, 1 to 2, 2 to 3, and 1 to 3, है ना? So from this 2 to 1 or this faulty to normal. So fault to normal. So these are the lambda 1 2 2 3 or 1 3 are the factors which we have to define here. So actually this will require again one whole lecture or detailed lecture, but just briefly I will just discuss this with you. So this military reliability handbook will give the idea about how to analyze the reliability in any fault tolerant converter design. So for the switch, we can find out failure rate of IGBT or diode. So first IGBT or this switch and diode. These are some empirical formulae given in this handbook only. So we have to refer this handbook only. So this is the basic failure rate. This is the quality factor. It is the environmental conditions factor like this. So based upon this, pi c is the contact construction factor. These are the fixed parameters actually, depending upon the switch data sheet. And this is the application factor. So these are the application rated output power PR, and pi a will be different for different ratings. So in this handbook, they have given these parameters range. So as per our application, we can decide those values, and we can find out this pi s stress factor as well based upon this empirical formula. And so for this pi t diode and switch, we can find out junction temperature of the switch will be find out from these different basic formula of heatsink design, and then average power dissipated in a cycle across diode or switch. We can find out from basic formula given in NADMON or any other good book. V into I. So these are the parameters which we have to consider from the datasheet also. So the datasheet of the switch will give you these values. So after having these basic calculations, we can find out for these data. These we can take from datasheet of the diode. These we can take from the datasheet of the IGBT, है ना? And these are the circuit parameters: voltage, load resistance, and load inductance. And based upon these, we can compare. We can find out different parameters. All right. So those are the different topologies for comparison. This is the single phase H bridge 5 level, the 5 level fault tolerant MLI. Then again third topology, and this is the 5 level FTMLI topology considered. And so after having comparison between these topologies, so based upon these formulae, lambda t, lambda d, lambda s, this pi s, pi a, pi t, diode switch, TJ, TC, PD switch, PD diode. So now for these parameters or these reliability parameters can be found from this for different topology and compare with the proposed topology here, topology 1, 2, and 3. So these are the values obtained here for that reliability factor. Now, yes, so this is the different case of the, this I will not focus on. We need to discuss that thing. Yes, failure rates we can find out. Failure rates can be given because time is now less. So I would like to just conclude this thing. Briefly, I will just tell you. In the simple converter topology, for example, we can take this cascaded H bridge converter 5 level. So in this case, how we can find out this? Lambda 1 2 is the probability of the transition from STI to STJ. That means switching state number 1, 2, 3, 4. है ना? So 1 to 2, 2 to 3, 3 to full failure. है ना? So 1 switch fault, 2 switch fault, 3 switch fault, or full failure. Or healthy, 1 state, 2 state, and full failure. So this is normal state, single switch fault, 2 switch fault, and full failure. So we can transit between among these 4 different states here. All right. So we can find out these parameters. Then after this, we can calculate those parameters based upon the military handbook of Markov chain theory using this formula. No need to remember this formula. We have to take this from that handbook or that reference guide only. And after this, compare these parameters for this number one topology, same things. Then for topology number two, again calculate those parameters. And now after this, compare all these. So this reliability of the four topology and various fault tolerance cases of proposed topology are determined, and this will give the clear picture about this thing. So this will give the total reliability factor with this time. So this picture will give the idea about mean time to failure rate. So you can say which topology will be giving you the good reliability. Then this is the topology number 3. So this will be giving this much. So reliability factor should be more for more time. So you can say after long time, after long hours of operations, this RT should be large. So as far as this concern, this topology number 3 is excellent. Then 2 and 1 are at this average, and other topology are having very less reliability after long run, you can say, after running the converter for long duration. So again, compare these with under different parameters or components: main switch, diode, capacitor, relays, reliability in on condition, open circuit or short circuit, power rated maintained or not. Yeah, this is again one thing. So in common language, if we don't want to do the Markov chain theory analysis, then in general terms we can say, okay, if power is maintained constant rated value, then system is reliable. Maybe with poor power quality, no problem, but you should get full power. So in this third, we are getting full power under all operating conditions, under all switch faulty cases. In topology number 2, we are getting full power partially, means under 50% faulty cases partially, 50% otherwise full. But also partially. This topology 100% full, because we are using one spare H bridge for the same converter, like this. So compare these, and I would like to just conclude this thing. So thank you so much for your attention, and now we are having some time for discussion. So just I will summarize this interaction. So I have covered basically I have covered today power quality mitigation via this new SST technology for future smart grid, and covered this SST concept, dual active bridge, multi-level, and reliability in power to converters. So now forum is open for discussion now.
Queries are invited, please. Anyone can ask.
I hope I have given something and means not very difficult. I tried, but maybe anybody.
Participants, please.
Okay, this is the work actually done by two of my students, one Deepesh, one Sai Krishna. So they got good publications as well based upon this work. So I thought I should convey this to the audience.
Yeah, good. So anyone having any question? Or Dr. Vikram, are you there?
Yes, sir. I'm here.
Okay.
Hello, Vikram.
Yeah, sir. Fine. How
Yes,
are
yes,
you?
yes, fine, fine, fine.
Yeah. So actually, I was waiting for your lecture to start,
Okay.
and we had a talk regarding some project few days back.
Yes, yes.
So actually, I've submitted this ERG this time today,
Yes, yes. Okay.
but we got this from Semicron only
Okay.
regarding
Semicron.
quotations from Semicron,
All right. Okay.
SSC and SSC drivers.
SIC be purchased from that is online
No,
only.
we are
Element.
not
Okay.
going for
Right.
purchase. We are just getting the quotation to put the price only. Yeah.
Okay.
So it's nice to have you again with us. Share
Thank you
your
so much.
knowledge, in-depth knowledge about these converters, their fault tolerant analysis, applications, and applications of all these inverters in respect of smart grid as well as other smart appliances like electric vehicles, and how to mitigate these harmonics, how to improve the power quality issues. We have taken lots of things. We have covered lots of things. I hope it will be little bit overhead for the students or the participants. That's fine, but they can have the idea
Huh.
what to do, how to move, because we are here just to give them a track, to
Huh.
show a path, not to teach here.
Yes, yes.
Just here to give a path how to move, what to do.
Uh, yes, yes.
That's quite fine. I find it interesting. I hope the participants also got it quite interesting. Definitely some research concepts will come out of it. Some will definitely try to come to work on it. So
Yes,
my
this is the way only. Yes,
yeah,
I also got when I was doing PhD, then that time I also attended some courses like this. So from so many professors, I got so many ideas.
yeah,
Even
yeah.
a single idea can change the world.
Yeah, yeah, just a single idea is required. Whenever
Yes.
somebody will ping, we can know.
Yes, yes.
This is something like PhD where he will stick or where he will ping it out. That is the
Yes.
important point.
Because main thing is that what to do in the PhD. So that issue, what to do.
Yeah,
So if somebody can give the idea, then your half work, 50% research is
work
over.
is done. Yeah, yeah. Mainly the problem finding.
Yes, yes, yes. So
Solution can be developed one or other way.
yes, yes.
Yeah. So again, my task is here as one of the coordinator of the same FDP.
Yeah, yeah.
So
Okay.
my
We
task
both
is
are coordinating this program.
Yes, yes, yes. I've seen that. Yeah.
so I thank you very much, sir, for being with us, giving your valuable time for the presentation. And once again, I thank you from the department side, electrical engineering and NIT Agartala, and the participants and the coordinators and all others who is working behind the screen, like the person who is doing the live streaming and who is arranging other things,
Uh,
like Rajesh,
yes.
like creating other what is called accessories, whatever are required to complete the program. So thank you very much, sir. I hope we'll get again your help wherever we are in need.
Yes, thank you so much, and thank you for calling me for discussing my research area, and thank you to Bikram and Arvind sir also for supporting
Thank you. Thank you.
continuously in my so many activities like conferences, reviews, and everything. Thank you so much for those activities also.
Yes, sir. Sir, sir.
Yes,
I will be here only,
yes, yes,
always.
yes, yes, yes,
This is
So,
nothing but a
okay.
collaborative work only, sir.
yes, yes, yes.
Now I request all the participants, please turn on your camera for the attendance. Everyone, please. Amtab, you just capture one that screenshot.
Yes, sir. Yes, sir.
And if anybody is interested to ask some doubts in future also, they can also contact me via
Yeah.
email ID also, no problem.
This is also available in YouTube. Live streaming is there. Students are
All
we
right.
are managing them.
Okay.
Okay, I am going to click.
Yeah, okay, good. Smile, please.
It is okay.
Okay.
Thank you.
So thank you everyone.
Sir, good night,
Thank you so
everyone.
much.
Survedi ji, and good night.
Good night,
Good
sir.
night.
Thank you, sir.
Thank you,
Okay.
sir. Good night.
Thank you, sir.
Okay, bye.
So now this is the time to disconnect offline.